We want to go ahead and take a look at inverses. Inverses of functions in particular, but relations also have inverses. Now, remember, a function is where every number you put in has one and only one number that you get out. So if I gave you y equals 2 to the x, we could go ahead and make ourselves a t-chart. So here I put down some numbers for x, take 3 and plug it in, so I'd have a 2 cubed, which you guys know is 8. Then I'd plug in 2, and I have a 2 squared, which you know is 2, or 4. Then 2 to the first. Then it would be 2 to the 0. Remember, anything to the 0 is 1. Then I'd have 2 to the negative 1. Remember, a negative exponent takes it and puts it in the bottom, so it'd be 1/2. But you can also take a look at the pattern here of 8, 4, 2, 1. In other words, you're dividing by 2 each time. So you'd plug in negative 2, 2 to the negative 2, you know it would be 1 over 2 squared, which is 1/4. Once again, you're dividing by 2 or multiplying by 1/2 as you're going this way, and then you get 1/8. If you go ahead and plot those points, you would get this blue curve. Oops, undo. Now, your inverse says if I plug 3 in, I need to get 8 out. That is your original function. Your inverse says I got to undo that. So in other words, I'd have to plug in 8 and get out 3. So your inverse here, instead of plugging in 2, getting out 4, you'd have to undo that. So you'd have to plug in 4 to get out 2. So in other words, your inverse is really just switching your x and your y values around. So if we plot those points, we're over 8 up 3. Over 4 up 2, and so on. Continue to plot those points and connect them, we get this shape here. Now, the way my technology generated my graph, it did not put arrows on the end here. It should be an arrow here kind of going up forever. Should be an arrow here going straight down forever. Should be an arrow here going straight to the left forever. And here it should be an arrow going up at an angle forever. So keep in mind that you should have arrows on those. Now, this blue inverse, or not the blue inverse, the original blue function, if I reflect it and fold it over this green line would give me the red down below. So looking at a graph, you can always find your inverse by folding it over the green line, which is your y equals x line. Now, looking at this here, for the blue, our domain is all real numbers. We could put anything we wanted in there. We can put in any number here because we're not dividing by variables. We're not having a variable instead of a root. But when you look at what you get out, you only get out positive numbers, those that are above the axes. You can never put anything in here and get out a negative because it's a positive 2 to some power. Now, looking over here at your inverse, well, gee, we go down, we get negatives, go up, we get positives, we go up and down forever. So our domain is, or not our domain, our range going up and down forever is all real numbers. But you notice your red graph only exists to the right of 0, so your domain is the positive numbers. So as we look here, what we had for your range of the original went to the domain of your inverse. And what was the domain of your original goes to the range of your inverse. So how do we find inverse functions if we're looking at table of values? Well, what did we do before? We just switched our x and y. We had also just said that the domain of your function becomes the range of your inverse. And the range of your original function becomes the domain of your inverse. And how do we find an inverse function if you're looking at the graphs? We had said that you just reflected over the y equals x line. But what do you do if you're actually looking at the equations and trying to solve it algebraically? Well, up here we had said we switch x and y when we're looking at the numbers. And really, for your range and domain representing x and y, we switched them. So that's what we're going to do here is we're going to switch x and y, and then all we have to do is solve it for y. Now, if your inverse function for f of x is either written as f with a little -1 exponent or f, and just a second here, there you go, or f with a little -1 exponent and then of x. The -1 does not go after the x, the -1 goes after the f. So, inverses exist of functions if they are one-to-one, meaning they have to pass the vertical and horizontal line tests to have an inverse function. Now, find our inverse of this. Remember, we had said when we're dealing with table of values, well, this is not really a table of values, but could easily be written that way. We just switched x and y. So we're going to switch our x and y values. Switch our x and y values, and switch our x and y, and switch our x and y. So what we have in red is our inverse when we're dealing with normal numbers. Now let's go ahead and find the inverse of this. Remember that that means it's really y equaling -2x plus 2. We're asked to find our inverse, so we need to go ahead and switch x and y. So interchange x and y. Then we need to get y by itself, so subtract 2. Then we have to get rid of the timesing by -2 to get y totally by itself. So you could divide by -2, you could multiply by -1/2, wouldn't make a difference. Multiplying both sides by -1/2, we would get this here. This is your inverse. Now typically you're going to write it as f with a little -1 exponent of x equaling -1/2 x plus 1. Go ahead and try this problem. So we get y equaling, because our function notation is y. We switch x and y. We now need to go ahead and get y by itself, so by subtracting 6. Then we need to get rid of timesing by 1/3, so we could either divide by 1/3 or multiply both sides by 3, and we would get this. This is your inverse. Being function g up here, we're going to write it as g with a little -1 exponent of x. Now, if you start off with two things that you're wondering if they're inverses, we can check that out. To check to see if they're inverses, we're going to take the one function and plug it into the other. In other words, it's a composition of functions. Our first function says 3/4 times your input minus 6. We're going to take our second function here, plug it in as your input. Well, our second function here in as our input here means it's going to go in wherever we had our x. Now if we distribute through, 3/4 times 4/3 is a 1x. 3/4 times 8 is 6. And then we still have our minus 6 over here. Well, the 6 is dropping, we just get x. If it simplifies down to just a nice normal x, that means what we started out with up here were truly indeed functions. Inverse functions, that is. If it does not simplify down to x, that means you either made a mistake or the two original are not inverses. So try this one here to see if they are inverses. In this case, I'm going to take the second one here, plug it into here to see what we get when we simplify it down. So we have 3 times our input plus 1. My input is going to be function g. So now I can simplify this down. I have x plus or x minus 1 divided by a 3 but multiplied by a 3, so those 3's drop. So I can just get x minus 1 with a plus 1, which the 1's cancel. So yes, these are inverses because it simplifies down to x. Check these last two. Are these two inverses? Well, you can take the one function, plug it into the other function, distribute through, collect like terms, we get this. Since it does not simplify down to just a nice normal x, they are not inverses.